Now in this third of this 4-part lecture for BIO367 on the fundamentals of microbial metabolism, we're going to talk about redox reactions and redox potentials and how we can apply those concepts to answering the question, could a microbe reproduce in a given environment? Let's refresh our memory on the idea of redox. So, oxidation-reduction reactions are ultimately how cells process energy. Many metabolic processes involve oxidation reduction or redox reactions. These are reactions involving electron transfer from an electron donating molecule to an electron accepting molecule. Each summed or total redox reaction consists of two couples or two half reactions, a reduction reaction and an oxidation reaction. So in this little cartoon here, we have an electron donating molecule shown over here in orange. It's got an electron and it is donating it to this green electron accepting molecule. So because this orange molecule is giving up an electron, it is being oxidized. Okay, so loss of electron is oxidation. Remember, Leo the lion says grr. Okay, this electron accepting molecule is gaining an electron, so it is being reduced. Right? Remember, gain of electrons is reduction. So on the left-hand side of the equation, we have the electron donor and we have the electron acceptor. And I cannot stress what I just said enough. Students always get confused about this. If I show you a chemical reaction and I ask you to label the electron donor and label the electron acceptor, they are always going to be over here on the left-hand side. They are the reactants. Okay? Always remember that. All right, let's think about this a little bit more. Here are some biologically relevant redox reactions. On the top is the reaction that we just worked through earlier in this lecture. It is aerobic respiration. So here's our old friend glucose. The chemical formula is written out a little bit differently, but that's C6H12O6. You can count the atoms if you don't trust me. Here's oxygen, here's carbon dioxide, here's water, and here we see energy. Energy is being released, and we know that that's true because we know from our delta G calculations that aerobic respiration is an exergonic reaction. Lots and lots of organisms use this as a way of making their living. Down on the bottom, we have a methane oxidation or methane respiration. This molecule right here is methane. Okay, it's reacting with oxygen to form carbon dioxide and water. So what is the electron donor and what is the electron acceptor? Methane is the donor and oxygen is the acceptor. Okay, and how do I know that? Well, I can look at the methane and I can calculate the reduction of potential associated with the carbon in that molecule, and I can see that it's going from -4 over here to +4 over here when the same carbons are found in the molecule CO2. I'm not going to review how to calculate the oxidation state of atoms within a molecule, but it is described in the appendix of your textbook, and you should have notes on that from your general chemistry classes. So for this carbon to go from a -4 to a +4, it's becoming more positive. So it must be losing electrons in order to get more positive. If it's losing electrons, then it's giving them up, and that means that it is the donor. It's giving away electrons. The oxygen, in contrast, has gone from a redox, an oxidation state of 0 to an oxidation state of -2, regardless of whether it's in CO2 or H2O form. So it's getting more negative, and in order to get more negative, it had to have accepted electrons. And when you accept electrons or gain electrons, you become reduced. So oxygen is the electron acceptor. Generally speaking, oxygen is a fantastic electron acceptor. It is the best naturally occurring electron acceptor on Earth, okay? Which is a big part of the reason why aerobic respiration, and it doesn't have to be with glucose, any kind of aerobic respiration is a fantastic way to gain energy. So another thing I should mention before I move on from this slide is that each total redox reaction has two half reactions associated with it, an oxidation reaction and a reduction reaction. So the methane to carbon dioxide reaction is the oxidation reaction, and the oxygen to water reaction is the reduction reaction. Those are the half reactions that, when put together, result in the overall redox reaction shown. So at its most fundamental, knowing whether or not a microbe can make a living, in other words, whether it can get energy from its chemical environment and use that energy to make ATP and therefore reproduce. We always have to look at the chemical mixture in which the microbe is found. So what is in the microbe's environment? And if we look at those chemicals, we have to ask, are they capable of giving electrons, or are they capable of accepting electrons? And that has a lot to do with who their neighbors are. So let's introduce a term, and the term here is reduction potential or redox potential, and it's given the value, or it's given the not the value, but the symbol E naught. Okay, and that's, again, the naught always tells us at standard conditions. So the E naught, or the redox potential of a molecule, describes its tendency to donate electrons. It's expressed most commonly in volts, okay, and it's a scale that has been developed relative to hydrogen, H2, okay, molecular hydrogen. The more negative the redox potential is, the more likely an oxidation reaction is to happen. In other words, a chemical that has a very negative E naught is a very good electron donor. So electrons will typically only move onto acceptors that have more positive E naught values. Okay, so electrons will only move from glucose onto oxygen because oxygen has a more positive redox value than glucose does. And I'm going to repeat this when we get to looking at the electron tower, and that'll give you a visual to help you understand this better. In nature, whether or not a substance acts as an electron donor or an acceptor usually depends on what other substances are in its environment and what their concentrations are. So these calculations can get really complex, and I'm hoping to keep them to a fairly sort of basic theoretical level for the purposes of our class. You can calculate for any given total redox reaction, you can calculate the change in redox potential, the delta E value, by using the equation shown, taking the redox potential associated with the electron accepting half reaction and subtracting the redox potential associated with the electron donating half reaction. Let's think a little bit more on that. Here's an example that actually does exist in nature. This is something that some pseudomonads, bacteria that are found in marshy sediments, have been discovered to be able to do, and also there's some evidence that microbes from other environments can do this. So this is the reaction of ferric, Fe3+ iron, and hydrogen to form ferrous, Fe2+, plus protons. Okay, that's the overall reaction on the bottom. Up on the top, we've got the two half reactions indicated. So here, okay, we've got ferric iron plus an electron becomes ferrous iron here. Okay, that is the electron accepting reaction, and it's most commonly written in the direction in which it proceeds from left to right. Okay, the E naught values associated with these are here, okay, 0.77 volts. And these are something that you can look up in standard tables. They're found in the appendix of your text and also in the chapter on metabolism for some chemicals. Just below that is the half reaction associated with the donor, the oxidation reaction. It's written backwards from how it actually proceeds in the Uber reaction down here at the bottom. Okay, so down here at the bottom we see that we've got H2 and it's being converted to protons, right? And up here we've got H2 and it's being converted to protons. They're written in opposite directions, but let's not worry about that. In this particular case, for this half reaction, there's a value of 0 as its redox potential. Okay. I've kind of got this in here as extra, and I'm not really sure. We can just kind of ignore that, okay? Not sure why I did that. So the overall reaction, again, is shown down here, okay? And we can calculate the delta E value using the equation that I mentioned on the previous slide. And the final E value is 0.77 volts. So notice that it is a positive delta E. Now, so what? Let's try to apply this to some of the concepts that we discussed earlier in this lecture. Well, the really cool thing is that you can use redox potential as another way to calculate free energy changes. And free energy changes will allow you to answer the question, can a microbe make ATP doing this? Or in other words, can a microbe make a living? Can it reproduce in this environment? So we can do this using the equation shown here. Let's do an example of this. This is the example that we just, wherein we just calculated delta E, okay? So you can go back to the previous slide to see that calculation again if you need to, but here it is here. Here's the answer, okay? Delta E was 0.77 volts. Note that it's positive, okay? And F, capital F in this, stands for Faraday's constant. You can look that up in any number of places. It's 96.48 kilojoules per volt. N is the number of electrons transferred. So what is that in this case? We can answer that pretty simply here because we've got a reaction involving ions. So we could just focus on the iron. We've got Fe3+, and it's being converted to Fe2+, right? So if you're going from 3+ to 2+, N in this case is 1, right? That's a 1 electron transfer. So delta G can be calculated by using delta G is going to equal -1 times 96.48 kilojoules per mole, or sorry, per volt, okay, times delta E, which was 0.77 volts. Whoa, I'm running out of room here, okay? The volts are going to cancel out, and we are left with an answer that is, let's see, I had calculated this earlier. Where did I put it? Losing track of my stuff. Sorry, here we go. It's -148.6 kilojoules. Okay, and because this was at standard conditions, we can also know that that's -148.6 kilojoules per mole. So that is a pretty negative value. So we have a negative delta G, which means it is exergonic. Okay, this is a spontaneous reaction. It can happen thermodynamically, and it's a pretty large value, right? The value is larger in magnitude than the -31.8 kilojoules per mole needed to make a mole of ATP. So in other words, yes, we could have life if we had this chemical mixture in the environment of a microbe that of course had the genetics and biochemistry that allowed it to make use of this thermodynamically possible chemical reaction.